Thank you to the organizers. It's wonderful to be here. Today I'd like to talk to you about an ongoing research program with Blaise Goudreau regarding holographic Fermi surfaces, mostly in pictures. The initial research question that we have is very simple. In which context do Fermi surfaces arise in holographic settings? And the answer to this question may actually surprise you. One might say it's unexpected. So the diagnostic that we use in order to see whether we have a Fermi surface is called the low energy spectral weight. This is a quantity that directly calculates the charge degrees of freedom at a given frequency and momentum, as evidenced by the spectral decomposition. And furthermore, it can be calculated holographically via the boundary values of bulk gauge fields. So just to set the stage, let's start with some past results. It was shown that when you have an IR geometry that is hyperscaling violating, the spectral weight is exponentially suppressed for any finite theta in Z. However, if you take this particular limit, Z going to infinity and negative theta over Z fixed, it turns out that these theories are more fermionic in nature and that we do find a low energy spectral weight at finite momentum. And since in these theories all the bulk charge is behind the horizon, we interpret this as perhaps there's a correspondence between the momentum space distribution of the boundary charge and a momentum space distribution of the bulk charge. I should say that this Fermi surface that I'm talking about isn't the typical type of Fermi surface that you see in free theories. So what does spectral weight look like in free theories? For free theories, it's basically this step function at 2kF. But what we're getting is more of a smeared Fermi surface, if you will. And one interpretation that you might have is since ADS-CFT takes place at large N, perhaps what we're seeing is a series of nested Fermi surfaces. It's one interpretation you could have. But the really interesting part comes when you compare the holographic superfluid to this case. So for a holographic superfluid, unlike the semi-local quantum liquid, you might not expect any spectral weight at all, because in this case, all the matter, the bulk matter, is manifestly a condensate in front of the horizon. But we do nevertheless find low energy spectral weight in this case as well. And this puts forth a series of questions as to how we should interpret this, as in how should we interpret low energy spectral weight that exists independently of bulk charge? What are the degrees of freedom could this spectral weight represent? And to what extent do bulk charge distribution properties represent those of boundary charges? I should say on the holographic superfluid case, these results are in the so-called transverse channel. But if we turn to the longitudinal channel, we find other interesting phenomena, perhaps even more interesting. So, for example, we find spectral weight actually over a ring in momentum space. So we find a Fermi shell, which one might say, you might interpret this as nested Fermi surfaces of particles and holes. And furthermore, in this channel, we find a finite K instability, which leads you to believe that we are not in the true ground state of the theory in this holographic superfluid case. And motivated by this wonderful cuprate phase diagram, which drives some of us in the audience, particularly this charge density wave phase, you might say that perhaps the true ground state of the theory is a spatially modulated phase. And in order to check this rigorously, you would have to probably construct such a bulk spacetime via numerical methods. But one step to begin to model broken translation invariance in the bulk is to add this so-called axion term, a scalar field that's proportional to the coordinates, and then see if these instabilities still exist. And that's what's going on now. Okay, thanks.
Questions? Concerning your finite K instability, at which momentum does that show up? Is it somewhere in that ring of that you showed? This.
Right. So yeah, it shows up within the ring. Within the ring.
Okay.
Yeah.
Roughly where?
Okay. Well, at first it shows up only in a particular parameter space. That there are parameters in the theory, like your scaling exponents have to take certain values. It's a rather complicated expression. I couldn't tell you exactly where, but I can show you. I have it in a different talk.
Okay.
Let us thank Victoria again.